All right, 115 students. Today it's time to talk about acid-base conjugates, and then after that I will give you a discussion about amphoteric species a little bit farther. As seen in the POGIL activity during class time, we learned about acid-base conjugates that conjugate acids are related to their bases by having one more proton than those corresponding bases. The reaction shown here with acetic acid and water has two pairs of acid-base conjugates. And if you can hold on to this thought, they're two substances that differ only by one hydrogen. You're on the right track. There are other examples that you can find in many acid-base reactions. So if you look for an acid and a base in each reaction, on the product side of the example, you will find their corresponding conjugates. So in this particular example, we have ammonia, which is a base reacting with hydrochloric acid. Surprise, it's an acid. The base is going to gain a proton, so this proton is going to be donated by the acid and picked up by the base. The base therefore turns into its conjugate acid, and the chloride left behind from the HCl is the conjugate base of that acid. Okay, now there are other types of acid-base conjugates that are similar to this. Notice that we often try to connect the pairs with arrows just to make sure we see which ones go together. So the ammonia with the NH4 is one pair, and the HCl with the chloride ion is another conjugate acid-base pair. The arrow on the left was just showing you where the hydrogen ion goes. So an example at the bottom is another one that's quite similar. Again, the acid is the red compound, namely HCl, and the blue compound in the reactants is the base. The base is anything that can pick up a proton. Well, if you observe to see what has transpired in the product side, the blue compound that has nitrogen and carbon and some hydrogens on it is going to be able to pick up a proton because it has a lone pair of electrons and turn into its conjugate acid, and leaves behind again the same conjugate base that was observed in the first reaction on this page. The chloride ion is the, I'm going to abbreviate now, conjugate base for HCl. Another pair. There are lots of different possible examples. Just trying to give you some more examples so these become more familiar for you. All right, two more acid-base conjugate pairs. Now, another example from the textbook. If you look in your textbook, you'll see exactly this example. It's depicted in a slightly different way, but it forces you to think about the definition of acid and base and decide which one is an acid and a base without always recognizing a formula. So the acid is going to be the one that is a proton donor, and it's going to be one on the reactant side and one on the product side. And think in terms of what it can do, whether it can give away a proton or what it does in this particular example. So if you look at the yellow and the white on the left, it picks up an extra white ball in this reaction. So it's one that has been gaining a proton, so that would be a base. And remembering the definition that the proton acceptor is a base, and so we'll put the label base by the yellow and white molecule here, which apparently is HS, and then the white and or gray, whatever you think it looks like, white and green molecule ends up as the green atom by itself, and so that means that it has given away the hydrogen ion in this example. So this will be the acid. The green and white molecule is the acid. If you want to put a label to it, it's HF. Oh, that sounds like an acid now that you mention it. But the other one could be if you weren't sure, because it says HS. In this case, it would have a negative charge, although that's not depicted in this reaction. The HF then turns into its conjugate base, namely the fluoride ion, and put that label on it, conjugate base, and the HS picks up the proton and becomes H2S, and that would be the conjugate of the HS sulfide. It's SH. We don't have a good name for that. A conjugate acid for that species. Another pair of acid-base conjugates. All right. Let's see. One more set of examples on this slide. What are the acids and base in each of these reactions? I'm going to label these without writing out the letters, but A will be for acid and B will be for base. BL means Bronsted-Lowry, which is the definition that we're going to use here, but don't worry about another definition. I'm not going to ask you for another. So looking at this particular example, the colors for the atoms are shown at the bottom. White again is hydrogen, black is carbon, typically it is, and red would be oxygen. So this first compound, if you were to give it a formula, it becomes HCO3, which is hydrogen carbonate, if you recall having seen that before, reacting with H2O, and the resulting products give you CO3 minus 2 carbonate ion, and the other product is, let's see, water has one more hydrogen on it now, so that's hydronium, which again, if you recall, has a charge of +1. So what has happened in this case? Which one is acid, which one is the base? Well, think about where the proton was donated from. So that would be the HCO3, the hydrogen carbonate ion, which turns into its conjugate base, the carbonate ion, so I'll label that as a conjugate base. That means that the other reactant, namely water, would be the base for this particular example, and it turns into its conjugate acid, namely hydronium. So there you have a pair of conjugates, of acid-base conjugates. Water with hydronium is one, hydrogen carbonate with carbonate is the second pair. The reaction in the bottom half of this slide shows another reaction, and it starts off with the same compound. It's still hydrogen carbonate, but what's happening to hydrogen carbonate in this example? In this example, it ends up as something else. Now it's H2CO3. We call that carbonic acid. You don't have to know its name, but notice that it now has one extra hydrogen on there. So that means that it gained a proton. So hydrogen carbonate was a base to begin with. The other compound is that HF that we saw in the previous slide. So that would be an acid, as it gave away a proton. And so the resulting compounds become the conjugates here. So hydrogen carbonate in this example is a base that has a conjugate, which is H2CO3 carbonic acid. The HF is an acid that turns into the fluoride ion, namely its conjugate base. Another pair of conjugate acid-base conjugates. Now we will use these to think about amphoteric species. And I'll jump to another slide here. Whoa. To extend this discussion, we'll think about water as having the capability of being both an acid and a base, depending upon the context. So the anion from an acid is going to be a base because it is a proton acceptor. And water can have an anion. When you have water in an aqueous media situation, it has the ability to dissociate. It splits apart to make two or more ions, but it doesn't automatically dissociate to make hydrogen ions and hydroxide, though you may have thought of it that way on occasion, because the hydrogen ion doesn't exactly occur by itself, which we discussed in another POGIL activity recently. Not 26, I think that number's incorrect. That might have been 28. And so the hydrogen ion instead is picked up by a second water molecule and becomes hydronium. So water has a dissociation process, back up, dissociation to make two different ions, but hydronium is one of them and hydroxide is the second one. It has to react with another water molecule for that to happen. So water can have the ability to both give up a proton and to pick up a proton. That property is what we call being amphoteric, or amphoteric, you may see it that way sometimes, but amphoteric is the one I'm going to call it. Sometimes an acid, sometimes a base. It depends on where it is. So if it's in a reaction with a conspicuous acid, then water will be the proton acceptor and water will be the base. And so in this example at the bottom of the slide, HCl is obviously going to be an acid. It's never anything else. And it gives away a proton to water where it's behaving as a base, turning it into its conjugate acid, the hydronium ion. And HCl turns into its conjugate base, the chloride ion. So here water is acting as a base. As I said, though, it depends on the context where you see it. If you put water with a base, water will give up its proton to the base. And so there's a couple different ways that can happen. Sometimes you'll have metal hydroxides where water is going to behave as an acid. A metal hydroxide is always the base. And in this case, the base is the hydroxide ion specifically because the metal is a spectator ion. And so the hydroxide turns into its conjugate acid, namely H2O, and this water turns into hydroxide ion, which sounds a little funny, but it has turned into its conjugate base. So in this case, the water has been able to donate a proton. The other example that makes it more clear than the first one, it looks a little funny because you got hydroxide two ways, is to use ammonia as a base. Ammonia is a compound that we will run into from time to time. Make sure you realize it's a base. And if it's a base, that means it can pick up a proton and turn into its conjugate acid. But where did the proton come from? It comes from water. So water is therefore converted to its conjugate base, hydroxide. That example is more conspicuous, but here water was an acid. So we've seen two examples where water behaves in different ways. So let's look at another one and see which way water is going to behave. If you put water with an acetate ion is the ion that results from acetic acid, related to acetic acid. In this case, the acetate ion is going to behave as a base. It's not got a proton to give away, but instead it can pick one up from water. And when it does, the acetate ion turns into acetic acid, putting that proton on the end of the formula. And water, having given away a proton, turns into its conjugate base. So here water is an acid. You have to just look at the example and see which way things have reacted to see who's the conjugate or which way they're behaving. And water has the ability to do both. So if we think in terms of some conjugate acid pairs, it will help us to discover which compounds can be amphoteric. What is the conjugate acid of each of these? Well, think about it for a minute. The conjugate acid of these species will always be the one that has, one more proton than what is shown in the formula. So add H plus to come up with the conjugate acid. So for each of these examples, HSO4 becomes H2SO4. The carbonate ion, well, that's called hydrogen sulfate, I should have named it. The carbonate ion becomes the hydrogen carbonate ion, which is now going to have a charge of -1 if you've added H plus to it. And the hydroxide ion, oh yeah, that becomes water, its conjugate acid. All right, now let's look at the second question. What's the conjugate base for each of these? So to come up with a conjugate base in each of these cases, you need to remove a hydrogen ion to come up with the conjugate base. All right, think a little bit, and you can do that, but pay attention to charges or you'll get them a little bit erroneous. It's easy to overlook a charge when you're not being a little casual. So the hydrogen sulfate ion, if you remove H plus, becomes the sulfate ion. Uh-oh, my tool is writing slowly again. The sulfate ion with a charge of -2. And then, I'm trying to make this right, sorry folks. Then water also has a conjugate base. If you take off a proton, it becomes the hydroxide ion. And so that's the last one. The last one has a conjugate base. All you do is take off the hydrogen ion, the proton, and your result from HCN leaves cyanide ion. Cyanide ion is a -1 charge after you've taken away H+. Now, looking at this helps us to discover which compounds might be amphoteric. So if you can give away a proton or pick up a proton, then something will be amphoteric, can act both ways. So which of the following can be amphoteric? Can carbonate ion give away a proton? Doesn't have one to give, so it can't be that one. Can hydroxide give away a proton? Well, it might, but in aqueous solutions, it's very uncommon to find oxide as the ion because any compound with oxide tends to be terribly insoluble. So that is not really a realistic aqueous species. So the third one is the best answer here because H2PO4 can act as an acid and give you hydrogen phosphate. Hydrogen phosphate has a charge of minus, get the number right, HPO4 has a charge of -2 when it's acting as an acid. It becomes that conjugate base, or dihydrogen phosphate can also pick up a proton and be turned into what's known as phosphoric acid, H3PO4. All right, so acting as an acid on the top example, where it gives away a proton, as a base on the second one, where it picks up a proton. All right, there we have some examples of amphoteric species. Another one on this slide, however, that wasn't in the last question, that is also amphoteric, and I'll mark it with a star, is one that's shown from questions 1 and 2, which can give away a proton and pick up a proton, and that would be the hydrogen sulfate ion. Hydrogen sulfate can both pick up a proton and donate one. Another one that's not shown here might be the hydrogen carbonate ion that was shown from a previous page, but the hydrogen carbonate ion would also be amphoteric because you could lose a proton or pick one up. Either way, that compound has two different possibilities. All right, I hope that helps you understand a little bit more about amphoteric species. Look for more fun things on the next mini recording.